So you're prepping for the BIT entrance exam and you're looking at that syllabus, right? It's just this huge list of topics: computer architecture, C programming, networking, and they can feel totally random. But what if they're not? What if all these things are just different stops on the very same road? Well, in this explainer, we're going to draw the map that connects all the absolute essentials of computer science.
I mean, seriously, you're trying to cram everything from computer fundamentals and number systems to C programming and networking all at the same time. It's so easy to get bogged down in the details of each one, completely missing the forest for the trees. And that's exactly what we're going to fix right now. We're going to see how all these concepts logically build on each other. We're going to build a mental map right from the ground up, starting with the machine itself and taking it all the way to the entire global internet. So, you ready? Let's jump in.
Okay, our first stop on this map has to be the most fundamental question there is. We have to start here because everything else, every app, every website, every single line of code is built on this one simple idea. So what is a computer, really?
Okay, so at the most basic level, every computer is just two things. You've got the hardware, that's the physical stuff, the metal and plastic and silicon you can actually hold. And then you have the software. Those are the invisible instructions that tell the hardware what to do. The best analogy I've ever heard is this. The hardware is a piano, but the software is the sheet music. It's what tells the piano which beautiful song to play.
And here's the really powerful part. It doesn't matter if it's your phone, a laptop, or some massive supercomputer. They all work on this same simple four-step loop. You give it some data, that's input. It thinks about that data, that's processing. It gives you a result, that's output. And it saves that result for later. That's storage. That simple cycle, that's the heartbeat of all computing, period.
All right, so we've got the big picture. Now let's pop the hood and move to our next section. What are the actual pieces inside the box that are doing all this work?
You know, to handle all that data, a computer actually uses a whole team of different kinds of memory. The easiest way to get this is to picture a workshop. That huge filing cabinet in the corner where you keep everything long-term, that's your secondary storage, your hard drive or SSD. When you need to work on something, you pull it out and put it on your main workbench. That's your RAM. The basic instructions for just turning the lights on in the workshop, that's built-in permanent ROM. And that tiny little tray right next to your hand holding the exact screw you need this very second, that's cache memory. Super fast, but very small.
All right, but software isn't just one thing, right? It's really split into two big categories. First, you've got system software, like your Windows or Mac OS. Its only job is to manage the computer itself. Think of it like the stage crew in a theater. And then you have application software, your web browser, your favorite game, a word processor. These are the actors on the stage, the ones doing the specific things you actually came to see.
Okay, so we get the physical parts, but here's the million-dollar question. How does a hunk of metal and sand actually think? How does it process anything? Let's move on to our next section and get to the very core of how a computer understands our world.
You and I, we live in a world with 10 digits, 0 through 9. That's decimal. But computers, they can only understand two things, on or off, yes or no. So they speak a language with just two digits, 1 and 0, and that's binary. So to a computer, our number 10 isn't 10, it's 1010. So what about hexadecimal? Honestly, it's just a shortcut for us humans, a more convenient way to read long strings of ones and zeros without our eyes glazing over.
So how do you turn simple on and off signals into running a video game? The answer is something called a logic gate. A computer's brain, the CPU, is built out of billions, literally billions of these tiny electronic switches. Each one just takes a couple of binary inputs, a 1 or a 0, and spits out a single binary output based on a really simple rule. Just look at this. This is the rulebook for a simple AND gate. The rule is dead simple. It only outputs a 1 if input A and input B are both 1. Otherwise, it's a 0. That's it. But, and this is the magic part, when you combine millions and millions of these simple gates with other ones like OR and NOT, you create circuits that can do math, make decisions, and render graphics. This is how simple on-off switches create the entire digital world. Okay, so we've got this amazing engine made of logic gates. Awesome. But how do we actually tell it what to do? In this next section, we'll see how we harness all that logic to make the computer solve real problems for us. Before you even think about writing code, you need a plan. And that plan has a name, an algorithm. Think of it as a very precise step-by-step recipe that you designed to solve one specific problem. Whether it's sorting a list of names or finding the fastest route home, the algorithm is the clear set of instructions the computer is going to follow to get the job done. So, we write these recipes, these algorithms, in languages we can understand, like C. But the computer, it doesn't get it. It only speaks machine code, those raw ones and zeros. So we need a translator. A compiler is like a book translator. It takes your entire program and translates the whole thing into machine code at once. And interpreter, on the other hand, is like a live translator at a conference. It translates and runs your program one line at a time. And boom, this is where all those topics from your syllabus finally click into place. They're just different tools for giving the computer instructions. C programming lets you write detailed recipes that control the flow of a program. SQL is a special language for giving instructions about huge databases. HTML is just a set of instructions for how to structure a web page. And things like stacks and queues, those are just clever instruction sets for organizing your data efficiently. All right, our map has taken us deep inside a single computer. For our final section, let's take a big step back and zoom all the way out. What happens when we start linking millions of these things together? So what is a network? Really, it's just computers talking to each other. The only thing that changes is the size of the conversation. The Wi-Fi network in your house, that's a local area network, or a LAN. A network that connects an entire university campus or part of a city, that's a metropolitan area network, a MAN. And that gigantic global network of networks that connects the whole planet, that's a wide area network, or WAN, which we all just call the internet. But wait a second. How do billions of devices, made by thousands of different companies, all speak the same language without it being total chaos? The answer is protocols. A protocol, like TCP/IP or HTTP, is just a shared set of rules. It's like the official grammar of the internet. It's the reason a request sent from your phone in one country can be perfectly understood by a server halfway across the world. And there it is. That's the map. We started with the physical hardware. We dove all the way down into the weird world of binary logic. We built our way back up with algorithms and instructions, and we connected it all together into a global system. You see how it all fits together now? It's not random at all. So, that long, scary list of topics for your exam? It's not just a list anymore, is it? It's a journey. It's the story of how we build our modern world from a single switch to a global web. You've seen all the building blocks. You have the map. So the only question left is, what are you going to build with it?